Okay, homework 4, part C. Our question is, ethanol reacts on a catalyst surface to produce acetaldehyde and hydrogen at 548 Kelvin and 101.3 kilopascal. The reaction is first order with a rate constant of 10 mole per meters squared per second mole fraction, or meter squared second mole fraction. The reactants and products diffuse through a 1 millimeter gas film with bulk gas composition of 6 to 2 to 2 mole percentage, ethanol, acetaldehyde, hydrogen, respectively. And then we have our Maxwell-Stefan coefficients, and we need to use solver like we did in part B to just show our answers. That's for part D. Sorry, I was just looking. I thought I had something written down, but not yet. So part C, what we have, what I wrote down here, the only thing I wrote down, because that's all we really need, because it's very similar to part B, but I have ethanol, which we're going to use as one, like in the problem statement, is going to react with the surface to make the acetaldehyde and hydrogen gas. So, we can start by first getting a driving force, for these problem. So our driving force, which we're going to call it just D1, is going to be equal to our dy1 over our dz, and that's going to be, the summation of, that's a j. Exactly what we did for homework, or this last homework problem, which is nj minus yj ni over dij times concentration. Okay, so that's our driving force, and like we already did it with homework 2, but I just wanted to rewrite it just because. So now we can find values for ethanol and acetaldehyde using our Maxwell-Stefan equations. So we can do that next. You can still see my iPad, okay. Right, okay, cool. So we can start with ethanol. And we could probably just copy these down from up, but I'm just going to go straight into multiplying it by our gas film, which we're going to use similar to the length in the last problem. So I'm just going to go straight into that. And if you want a simpler version, you can watch the last video. And then we're going to have, our, since this is for ethanol, we're going to have y1n2 minus y2n1 over cd12. Oops, we got to add our other term, our 3 term. So we're going to have y1n3 minus y3n1 over c, should be 1, d13. Okay, so that's our ethanol term, and then we can do our AA term. And we're just going to basically just copy exactly above, but change the 1 for 2. We have y2 n1 minus y1 n2 over c d12. Jeez, why do I keep doing that? And then y2 n3 y3 n2 over cd23. So there's our 2 terms, and we're going to be using these terms in the Excel. But before we can move on to Excel, we also need a something for our guess cell when running solver. So we can do that. Oh, my thing fell, or my face cam. second. You can see my password. Okay, cool. Hopefully I'm still recording. I can't tell. Did that not work? Okay, still recording. Good. Sorry about that. So we can start with our n term like I was saying. So we're gonna have our n1, and that's gonna be equal to PD12 over RT, and then times our film. And then also, before we can start, we have to define our y1, 2, and 3. And we can get y1, because we know y1 is equal to, we know y1 times Rm is equal to our reaction rate. So we can solve for our y1 by doing y1 is equal to the absolute value of molar flow rate over our reaction rate. And then y2, we still need to solve. We can't really solve for it, so we're just going to define it as 0.5. Yeah. And then for y3, we're just going to be doing 1 minus y3. Oh, sorry, y2, not y3. So, that kind of does everything we can do on my iPad, so I'm going to switch over to Excel, and we can finish plugging in our values and running solver. Okay, I moved everything over to our Excel now. So as you can see, I spent some time and I've already added most actually of our constants from the problem statement. So we got pressure, temperature, we have our, well, R is known. C, we have here concentration, we have our coefficients, we have our given mole fractions, and then here we have our guessed cells, and then reaction rate, N1, N2, N3, and D, which is just our length, basically, or film thickness. So, I don't think there was there any actual formulas I need to show before? Okay. Yeah, here, Y3S was just calculated as the above 2, 1 minus the above 2. Then our reaction rate was 10, and then we found our N1 by using this formula above. So we have our concentration multiplied by our D12 in the numerator, and then divided by our RTD in the denominator, which I showed on the last video, or last part of this video. Okay, so I just had a placeholder DZ here, so I know where what to start with, so I didn't blank in my brain. So I think that's good. So what we're gonna start, we have to define these as formulas before we start, so we're gonna go here and then go to formulas, create from selection, left column. Okay, so now we can use those formulas in our rest of the Excel. Okay, so we're gonna make a counter in our DZ from 0 to 1000. So we're gonna go 0, 1. Let's just go to home, I think. Format, is that format? Insert, yeah. Is it here? Where is it at? Or insert. Where is it? I forget. Here, no. Oh, right here. Here it is. Series, column, step value, stop value at 1000. So now we should go, hopefully we don't go any further. Okay, cool, we got our counter here, and our DZ, and then, actually we'll make our counter over here instead of DZ, because our DZ we're gonna have to calculate a value in, I forgot. Control C, there we go. Delete, Control V, Control V, Control Z, Control C, Control V. Excel takes a lot of patience. Okay, there we go. And up here I'll just put counter. That's where I messed up, because I know when I don't label stuff I do it. So for our DZ we're gonna have it equal to our D value divided by 1,000. And then we have to multiply that by the counter for it to work. Make sure that, and it should stop at our film thickness, hopefully, or at least it should. Yep, at 0.001. Make sure that's our film thickness. Yep, okay, looks good. So after that, our next column is gonna be y1, y2, y3, y1, y2, y3, and we're gonna have dy1 over dz. Good, okay. And we're gonna have dy2 over dz. And then for our y1, we can just add our y1s here over, or sorry, over here over. Sorry, my throat's like going through it. Let me take a drink. Okay, so for y1 we can just do equals b14 equals b15 equals b16. Actually, for y3 let's do equals 1 minus this minus this. Okay, cool. Looks good. And then for our dy1 dz, I'll throw a picture up on the screen right now because I don't have it, but we're just going to be doing the thing that we just did in step, or the first part we're going to be writing down. I have it written down already because it's just easier for me to do it, because I don't have it pulled up, and otherwise if I would have to go from here to my Outlook like I've been doing, and I forgot to do that, so we'll just do that quick. I'll write it. I have it written down, so I'll just do it really quick. So we're gonna have our dy1 dz is equal to our d2, which is our y1 multiplied by our constant, oops, minus our y2 and then multiplied by our concentration times our coefficient, and that's going to be added to our y1 again. Sorry, kind of zoned out for a second. Subtracted by our y3 divided by our concentration. Okay, I do have a period. Times our coefficient, last coefficient. Is that right? Seemed to work. Hopefully that's the right value. No errors, so it looks good. And then we can do our dy2 over dz. I'll try to do this one a little faster, hopefully. Okay, there we go. Sorry, my throat hurts really bad. So we have our y1, y2, y3, dy1 dz, dy2 dz, so these can be copied down. We're not going to have a value yet because we haven't done this section, but it's okay. Yeah, okay, looks good. So our y, for our second part of y1, it's going to be equal to the cell above it. We don't really need a parentheses. Cell above it, and then that's going to be added to our counter, multiplied by our dy1 dz. Okay. Something seems off. I'm going to continue going, but once I get this part done, I'll double check everything. For our y2, we're going to get above, and then we're going to add that to our counter, and then multiplied by our step, or our dy2 over dz. Okay, and then here is just the same as here, so it can be dragged down. Then we'll copy all these and drag them down. Okay, there we go. 50-50. I'm just checking these values to make sure they logically make sense. I mean, it's not looking horrible right now. Okay, I'm going to double check everything and make sure it works, or make sure it looks right, and then I'll be back to run solver. Okay, I was able to find the problem. It was just when I was writing these down, occasionally instead of putting a multiplication symbol, I would put a addition symbol, so that was the whole problem. So now we have our everything in our sheet right now is correct. So we're putting okay. So what we can do now is we're going to copy our y1 and y2 values. So we're gonna, over here we can just put our y1 value at our bulk, which is going to be G of 1002, I think. Yeah, and our H value at 1002 or at bulk. So that looks good, and then you don't need our I-1002. So we can do that's going to be 0.6 of our total, and we said this would be 0.2 of our total. And then we can do this, and then minus this squared. So that's our squared value. And then there we go. And then we can just do the sum of these to get our sum squared value. And then that's what we're going to use for our solver. So now we can go into solver. So data solver. And we can go to, we want our objective to be the cell it already is, looks good. And then we want our range to be, why is it going like that? We want our, okay, so that's wrong, okay. We want our range, why is it doing that? I might just have to type it out. Hold on, let me try to fix it, I'll be back. Okay, I'm back. I couldn't get it, so I'm just gonna have to change it. So we're gonna do Y1S, so we're gonna need B14 and B15. So 14, 15. and then change this to B. Hopefully this works. B. Okay, GOG nonlinear solve. Give it a second. Okay, hopefully we'll see this works. It's not looking good. Maybe though, we'll see. Let's look at the bottom. No, that's actually really good. So we can see here we got what we wanted, which we got our 0.6 for Y1, we got a 0.2 and 0.2 for Y2 and Y3. Everything else is good, our values are good. Yeah, so everything seems to be looking pretty good. So that's how we did part one. Let's get part one. Read our problem. So we did everything here. For our part C, what is the reaction rate per area of catalyst? Here we go. What is the surface mole fraction of ethanol? There we go. So now we just need to vary the surface reaction rate constant to show and explain the extremes of diffusion and reaction limited operating conditions and its impact on surface versus bulk mole fractions of ethanol. So how we're going to do that is we're going to have to change our N1. We're going to change our N1 to, instead of this value, ooh, that might screw everything else up. That's okay, we'll have to fix it, I guess, maybe. But we're going to change that, and we're going to do our, equal to our reaction rate. And then, multiplied by our Y1S. Okay, cool. That did do what I wanted. So, as you can see here, when we change that value, not much changes, but as we start to go down, we just get our -1, which means that our reactant, we have -1s for our reactant, and we have 1s for our positive. So what that's kind of just showing is it's going really, really fast, so it just wants to be pushed completely to the product side. And then if we were to change it, say, like, to just a random number, like, we just change it to, like, a random low number. Let's do, like, 0.01, maybe. So we can see same, and then as we go down and down and down, so this might not be a good example because it goes negative, but hold on. Cool, same. And then as we go down, it's changing, but at such a small value that it doesn't even really do any change at all because our reaction rate is so little that it is just not really reacting. So yeah, that kind of shows how when varying the surface reaction rate, how our bulk and our surface fractions vary. Okay, cool.